Hello. Yes, thank you for being here. My name is Olivier. I'm currently a postdoc at Princeton, New Jersey. And today I wanted to give a synthetic discussion, sharing my own insights about a particular type of computation that often occurs, namely the appearance of a particular way in which cosmic relics appear in theories that contain scalar fifth forces. Um, and I'm going to have sort of try to have a parallel discussion. The scalar fifth force can be in the standard model sector, or it can be an element of model building in the dark sector. I should say this is probably more of a week 2 topic based on the organization of the workshop. This is going to be primarily early universe stuff, not a lot of discussions of late universe. But nevertheless, I think the questions that animate me animate probably everyone in this room. For example, how was dark matter produced in the early universe? Does that matter at all? Do we have an actual observable of this cosmological production? And then on the and is that production tied to the standard model? And on the other hand, of course, there's been a lot of discussions of dark sectors. Is the dark matter, a complex sector? Which I like to operationalize this question, as will be clear, by counting the number of fundamental constants that would define a dark sector. I mean, the standard model has 19 to 23 parameters, depending on how you count. The most vanilla theory of dark matter has only one fundamental constant, the fundamental mass of the dark matter particle. Now, there are more fancier theories, but if our prior is the standard model, more numbers should, I think it's fair to say that more numbers likely describe the dark sector. So in relation to last week, we had one of the aims of this workshop is to write a white paper. I believe there's a session also about this tomorrow, if I'm correct. And one of the slides that were shown were an outline of various topics that we wanted to include in such a paper. And 3 of them captured my attention because they're relevant to my work. And they were listed separately. So they were light but massive relics, long-range forces, and varying fundamental constants. And the fact that they were listed separately probably simply had to do with the fact that you're putting things on a slide for a discussion. But I think it's also telling because I think, at least personally, it's very tempting to try to think of these phenomenological bits sort of independently. I want just to leverage fifth force, for example, if I want to enhance structure, or I just want a theory that changes the fundamental constants of the standard model, for example, because I'm interested in doing something to recombination. So they're listed separately, but of course, for example, a new force would mean a new boson. And so it's a fair question to ask, was there a cosmological abundance of that boson? There's what I call the lesson from Maxwell, which is that forces are not passively tied to matter. They also have their own dynamics. In other words, background dynamics, they gravitate, etc. If you're focused on the varying fundamental constant side, then most consistent theory of dynamical fundamental constants imply, in fact, the appearance of a new field, generally a new force, also that can depend on the functional dependence of the constants. And so therefore, we have a new force. This brings us back to point 1. So there's basically a graphic formulation of that argument, which is that in field theory, you define a theory by a vertex. And once you have a vertex, you play Legos with them. You assemble them, right? So the light but massive relics, if I have a theory that couples to a particle, a scalar that couples to, in red here, that couples to a particle, whether standard model of dark, it can be produced by the particle, probably is a question I can ask. It can also have some initial conditions given by God, I suppose. It could have just put in the cosmic abundance of the particle there. The same vertex will give you a long-range force, and then if this field is considered a background field, this would be the diagram schematically representing the modulation, for example, of the mass of a propagating particle in the background. So focusing on the relic production, I would say there are many mechanisms for relic production, but sort of the big 2 maybe are thermal relics on the one hand and misalignment. So in thermal relics, I would say the tool of the trade primarily are some version of kinetic theory. The mediator is treated in kinetic theory. You're going to look at the Boltzmann equation. You're going to do something like freeze in, freeze out, etc. Then on the other hand, you're going to have something like misalignment, where your primary tool is the Klein-Gordon field equation. With a potential, you can maybe play games with having a more complicated potential or multiple interacting scalar fields. The paradigmatic examples, for example, of course, being misaligned axions and out. And the mechanism I want to emphasize today is sort of the mashing of these two, can be conceptually understood, I think, as the mashing of these two processes. And so sometimes it's called thermal misalignment. And in an effort to graphically say what I meant, I sort of put, I think, two sort of pictorial ways of thinking about this. If you like to think about the misalignment mechanism, in the traditional misalignment mechanism, the initial conditions are provided by, are essentially given by some other physics. In this case, we think that we're going to couple our particle to a thermal bat, and this thermal bat is going to provide a thermal force that will misalign the scalar. On the other hand, if you prefer the sort of Feynman diagram particle physics picture, I will say that now you're essentially doing a form of thermal field theory or kinetic theory in a gravitational background where Hubble can have can be parametrically large relative to other scales in the problem, in particular the mass of the particle, the scalar. So basically, the too long didn't read version is like, I would like to argue that a good way of building theories with scalar carriers is to promote the fundamental constants of a theory, of an existing theory, which we'll call the source or sector theory, to depend on the scalar. The sourcing of the scalar in not only cosmological context, but really many contexts is then tied to the thermodynamics of the source theory. As a result, in such theories, the early universe can act as a coherent, and the more coherent is important, source located in the distant past, which displaced the field in the past, resulting today in a relic energy abundance in the form of a coherent oscillations in the mediator from time Hubble equals parametrically equals the light mass onward. So in the context of studying this, it will be important to try to characterize the early universe as a source in the past, as a sort of a multi-component macroscopic source, which, depending on its phase of history, will have, of course, a non-relativistic matter phase at late time, relativistic free matter component if you ignore the gauge interactions, and a relativistic, and can be, of course, viewed as a relativistic gauge plasma with all the gauge interactions. And the kicker is that, in particular, if the scalar couples to this type of thermodynamic phase through the modulation of the gauge couplings, for example, then the early universe can, in fact, very efficiently produce a cold relic that is cold at production, but where the particle mass is as heavy as Hubble at reheating. Okay, so we'll say this. I like to present things sort of in a synthetic pedagogical discussion, but I would be doing a disservice to my co-author if I did not advertise our own work on this topic. And so myself and David Cincinnati's have written two papers on primarily focusing on the idea of couplings on the standard model side, which would provide, well, I would say that paper is mostly about looking at overproduction and perhaps some guarded statements about whether this is a viable dark matter candidate. We're very happy. The joint PRD, PRL came out last week. And then there are many elements of discussions available both on the standard model side and on the dark sector side, and many other papers, some by authors in this room. And so, yes. So, okay, so for my discussion, I'll use some, my sort of thesis is that, yes, relics, forces, and fundamental constants are also sort of neatly tied, and so you can pick your favorite entry point in the discussion, and so I'll take dynamical constants as my theory entry point. So why consider dynamical constants in the first place? Well, because it's worked before, it's worked really well before. The Higgs mechanism is an example of promoting the mass of, at the time, the Z and W, and in fact all the fermions in the standard model to field-dependent quantities, namely the value of the Higgs field. But even before them, I think there's a very nice effective field theory way of looking at these things that dates back, in fact, to 1912, Nordstrom's theory of gravity, which I like to introduce this discussion with. So Nordstrom gravity would today be called scalar gravity, as opposed to GR, which would be tensor gravity or scalar tensor gravity. It was published in 1912, and so remember, special relativity is 1905, GR is 1915. So in 1912, the question of the day is how do we make Newton's equations Lorentz invariant? And the reason perhaps I'm obsessed with this theory is I feel like if I had been sitting there, that would have been my guess and I would have been wrong. But what he did pretty much is he said, well, I'm going to turn the Laplacian operator, I'm going to make the field dynamical. I'm going to say that scalar Newtonian potential is a scalar field. I'm going to give it Klein, well, I guess they weren't called Klein-Gordon back in the day, but Lorentz invariant dynamics promote the gradient to the triangle to the box. And then since the Lorentz invariance of the theory that characterize a particle as the mass, I'm going to promote the mass to being a function of the scalar field. In this particular case, all the masses needed to be promoted to the exact same function because of the namesake of this building, because of Strong's constraints from the universality of free fall. Now, of course, it doesn't work. I mean, we know that the true theory of gravity is GR. Particularly, it doesn't bend light, which is in fact, it doesn't interact with pure radiation, which is in fact that will come back later. But I really think it's a useful template to think about. And these particles are these kind of scalars are sometimes called dilatons at low energies. So how can we sort of rehabilitate this theory? Well, we can look for subgravitational couplings. So we are going to make this function multiplied by d, where d bigger than 1 essentially means a weaker force than gravity. We can try to hide the physics by adding a small but finite mass to the propagation of the scalar, in other words, the range to the Yukawa potential. And we can allow ourselves to give up on equivalence principle. We can allow different components to have different couplings. And so that's sort of Nordstrom recipe of building scalars is take a theory that you like, take its fundamental constants, make them functions of the field. Now, Nordstrom's theory is only about masses, but of course maybe masses of, well, the Earth probably, or atoms maybe, but of course in our modern understanding, we know that every mass of stable matter really is a function of the underlying constants of the Standard Model, some of which are dimensionless couplings. And so we'll sort of go a step further and say, well, we're not just going to promote masses to to field-dependent things. We're also going to allow ourselves to promote, in this case, the fine structure constant and lambda QCD, or equivalently the strong gauge coupling to functions of phi. And so in the field theory language, this means that the scalar now couples to the photons or the gluons, as well as the electrons and the up and down quarks. We don't have to stop there, but the reason people typically stop there is because this is pretty much the description necessary if you're going to do experiments in the lab. Stable matter is this is the recipe for stable matter. That's sort of the end of it. Yes? The disproportional to? You mean other functional, like quadratics and et cetera? So that's absolutely right. From a bottom-up perspective, I think you can sort of write any function you want. From a top-down perspective, the exponential form is preferred because you can argue it descends from string theory, although this is really only true at tree level. But you're correct. So I should really put an approximation sign here and say that whatever function you have, we're going to look at sort of a Taylor expansion around the vacuum of the field, and assume that the leading order term is more important than the rest of the expansion. All right, which will place a limit to how far of a field excursion we can do without leaving the regime of the theory. You can play the same game in the dark sector, like I said, to the extent that CDM theory is defined by one fundamental constant, promote that to a field, and this is in fact the sort of model that Marco and Diego and other Marco, I don't see him, I've been looking at, but that would presumably give you a force between dark matter particles. Okay, so the primary signature. So I kind of want to look at a very simple calculation that an undergraduate could do, but with a lens that will hopefully serve us later. So the primary, those might be called fifth force theories because the primary signature is that microscopic bulk matter distribution will source coherent field configurations. So the basic thing is you're looking at the basic signature is people are looking for EP violation around the Earth or the Sun, and so they look at what is a time-like spatially finite source made of multiple components, and then you solve essentially the Poisson equation, where you sum over each atomic source term of the star in this case. In the experimental context, you're concerned with the motion of a test particle, and so you would go basically use F equals ma, and that's how you would that's how you, for example, in using torsion balances and et cetera in the lab today, we're able to put extremely strong constraints or on equivalence principle violating forces on standard model objects. Yes. Mm, absolutely true. So that's correct. You would have, right, because the right-hand side, of course, comes about by hitting or you can see it here, both these equations of motion come from differentiating the mass function with respect to the field. And so the right-hand side may itself be a function of phi. If it's linear, then the derivative kills it, so you get there. In the other case, you would get, for example, if it were quadratic coupling, you would get a loop level force, or you might get a force in the background, essentially by cutting the loop, and if you have a passing wave of the scalar or a passing configuration of the scalar, it would manifest as a force between objects in that path. So this is kind of a spatial misalignment mechanism, if you will. I mean, locally, you can view this as, well, there's a bare potential, and then the source, the finite extent of the source essentially locally displaces the field, and you can view it as either giving an effective potential or biasing the potential or providing a force. And then as you, for an observer that is some distance away from the source, well, of course, so the field is displaced at the location of the source, and it has to be restored to zero far away, and it can't do that instantaneously because of dynamics, so because of gradient terms in this case, and so the propagator is the thing that relates the value of at the source to the value far away. And I mean, this is kind of taking a bazooka to kill a mosquito in this case, but this right-hand side, because it is the density of the sum of our atomic densities, is properly a quantity that belongs in kinetic theory. I mean, it's the energy density computed as the integral over momentum of the distribution function. Right, okay. In this context, you don't really want to think about it like that, but in principle, this is what it is. And so you have a situation where you're solving a dynamical field equation with essentially a thermal source, if you will, or a source that is computed using the tools of thermodynamics and thermal field theory. Another perspective you could take, which I don't think is one we could, but is sort of the alternate view of, you know, thinking in terms of Feynman diagram and viewing the potential of the sun as the coherent addition of individual particle processes. It's instructive to think that way, but it's calculationally not the best way to do things. I mean, it's very inconvenient. You wouldn't do it, you know, you can give an undergraduate this calculation and they don't need to know about Feynman diagrams and et cetera. What they would essentially do is, you know, use an EFT type formulation to go from the microphysics to the macrophysics and essentially build an EFT for the sun, for the source term, right? Okay, so what about cosmology? That's the discussion of sourcing the field in sort of laboratory experiments. What about cosmology? Well, like I said, we've got these three types of observable, and I think if you have a theory of fifth forces, I think it's natural to think that the long-range force will be the biggest impact on structure. At least naively, you think, well, dark matter attracts itself, forces have to do with the growth of structure. But as we've emphasized in many points last week, in fact, the homogeneous dynamics, the background dynamics, as opposed to the dynamics of the perturbations, are often what ends up driving most of the cosmological constraints. So actually tends to matter the most. Why can it matter? Well, in the case I'm going to emphasize, there's a risk of overclosure. In particular, like I said, the amount of relic production will be tied to the reheat temperature, the H reheat, if you couple to the standard model. And so combinations of couplings and high reheat temperature will produce too much dark matter. So you could at least think about getting overclosure bounds on your model space. Yes? Essentially. Good. We'll get to time dependence, right? So, because of course, in this case, in this simple calculation, the sun itself is almost static. So you start with Klein-Gordon, but you kill the time different derivative. The cosmological calculation is the exact 90-degree in Lorentz space version of that, which is why I sort of start there. So we'll come to the time dependence in two slides maybe, or a few slides. And then the other way you can impact the cosmology is you can impact structure, because this relic, if it has non-trivial behaviors, can impact structure to its modification to the Hubble law. So precisely like Mustafa asked, basically, I want to take this problem and flip it around. And instead of doing a sort of time-like, spatially finite source, I want to do a space-like source in the distant past. And so I want to have a view of the universe as some sort of a unique, a macroscopic source, a multi-component macroscopic source that lives in the distant past and sort of dims away as the universe redshifts. Of course, a big part of the challenge is that, well, if you're going to do the sun, well, the sun is hydrogen and helium, and that's about to a very good approximation. And the universe, up until, pretty far back in the past, is in fact well approximated as hydrogen and helium, but eventually the more exotic guys start to show up. And so characterizing this as a multi-species coherent source sounds like it will be a challenge, especially since I don't even know how far back I need to go. We don't know actually how hot our universe got beyond BBN. So we do know it needs to have gotten hot enough for thermal BBN to have completed, which places a bound at about 4 MeV on the reheat temperature. But we don't know much about the universe with certainty before then. Now, why would I think that would work? Why would I think that maybe a large relic is going to be produced? Well, what is striking about this this calculation with the sun is it couples to the bulk density of the sun, unlike ENM, right? The sun's neutral. And in the same way, the universe, the early universe, under a vector charge, any vector charge is neutral. Scalars are weird. It's also why they make passable candidate for a theory of gravity. That's why Nordstrom, well, I'm not sure he phrased it that way, but so tensor famously couple universally. Scalars need not couple universally across species, but within each species, the matter and antimatter source the field in the same way. This means that if I have a universe that is mostly photon today and I run it back, I produce electron-positron pairs, for example. If this were a photon, if this were a vector, wouldn't do anything. The charge would be conserved. I would have neutral before, neutral after. But in this case, I suddenly go to a place where in the past, a scalar charge just has appeared out of nowhere, right? The word charge is used loosely here. It's not actually a neutral charge. But anyway, I have the possibility that the macroscopic universe actually sources the field significantly. Cancellations are possible. You could say, well, what if the electron sector exactly cancels with the muon sector? Well, fine, but then the muons drop out first, right? So there will be a period of the universe's history where only the electrons are going to be around, right? So even exact cancellations, well, first of all, you might be suspicious. Well, okay, I don't know. Maybe you can do bottom-up model building and then make the charge exactly cancel. Maybe it's more plausible to think they would be equal, in fact. But exact cancellations are possible, but hard to maintain for sort of cosmic history. Okay, so quick review of standard misalignment, which I've already hinted at. Mustafa asked about time dependence. So now we're taking the zero mode of the Klein-Gordon equation. So we're killing all time derivatives. We're in an expanding universe, primarily radiation expanded universe. And so we're solving the time dependent Klein-Gordon equation in this background from some initial conditions from the field. At early times, when Hubble is small relative to the mass, the field is cosmologically frozen. Once Hubble passes the mass, the field starts oscillating, and the energy density it contains redshifts like 8 to the minus 3, which, at least at the level of a background, looks like a dark matter component. And just in terms of parametrizing the final abundance, we don't really parameterize the final amplitude of the field. You want to parameterize its final energy density relative to the total dark matter. and basically you've got this functional form, but it's all that to say that we're using an angular variable as a proxy to essentially define how much, what fraction of dark matter is contained in this coherent oscillation at late time. The thermal misalignment mechanism is essentially postulating that the field started at small initial conditions, was pushed somewhere, was eventually released, again at around the time h equals m. So from the perspective of the late time universe, it looks as if you didn't know about so it is pushed because it is coupled to some effective potential to determine of the universe. From the perspective of a late time universe, it looks as if we didn't know about the coupling. It looks as if the field had been originally misaligned. And so just an analogy with the previous formula, we define an effective misalignment angle, which is only a quantification of how much relic density you get. Okay, so now the correct source term. So my original impetus was to say, well, isn't it, I do my fifth force experiment with the Earth. I put the density of the Earth there. I run it backward. It's going to be the density. Densities are really large in the early universe. But of course, that was a bit too naive. The fact that the scalar is sourced by the density of the Earth, or by matter densities, is really only true in a certain non-relativistic limit. And so how do you obtain the correct right-hand side for the coupling of the scalar? It's very non-trivial, in my opinion. This is a beautiful result by Weinberg and Jakiv, which involves doing essentially integrating out the thermal sector in the path integral. And the result of it is that the effective potential is essentially, well, it's the grand canonical something. In a homogeneous system, it's the pressure. It's the total pressure of the matter that the field is coupled to. And it gets even easier if the field only enters through the fundamental constants of that sector. Because there are a lot of computations of pressures as a function of the fundamental constants. I mean, the pressure of QED is a function of temperature, mass of the electron, alpha. Okay, well, if the only way the scalar enters is through ME and alpha, I can take my answer that I know and love from QED, which is itself non-trivial to compute. I mean, you need to go to a plasma physics book or something and just substitute the functional form, and that gives me my equation of motion for the field, right? Okay, good. So now we're interested in what this guy looks like, this pressure term looks like. Yes? Good. So in this particular case, we're saying, so there's a couple of, so you could have a bare self-interaction potential, which for the purpose of calculation, we're going to ignore, but after the fact, you can, again, it's going to be, the importance of self-interaction is going to be a function of the excursion of the field. So we'll need to, I'm not sure I'm going to have time, but our results will be qualified by, essentially there will be, the self-interaction, at least a quartic self-interaction, tends to reduce the relic abundance, for example. You also get self-interaction through the thermal effects. In other words, like pressures are generally not linear function of fundamental constants. This means that even if your fundamental constants are linear functions, the potential is nonlinear, the thermal potential is nonlinear. But again, this is only a function of how far the fundamental constants themselves undergo an excursion during the dynamics of the field. So really, this calculation is analytically under control for small excursion of the field in the sense that they make the fundamental constants of the standard model in this case, or the dark sector, move minimally during the dynamics. Okay, so now I'm interested in studying, the potential of the universe. Sorry, the pressure of the universe. Yes. Sorry, phi is the scalar field. Phi is the scalar field. There's no, this is, phi is a function of t only. Well, sorry. This equation, if I reestablished the spatial dependence, it would be true. I could write a space-time dependent version of this. I would have the spatial pressure field. I'm essentially looking at the background pressure here, so the zero mode of the pressure coupled to the zero mode of the field. But there is uh, the space-dependent version of that equation also. Yeah. And of course, this is sort of the reason you're able to integrate the thermodynamic sector. You're essentially assuming doing this integral that the field is a constant, which means that the field, this is a background field approximation in the evaluation of the potential. And so this means that the scales associated with the scalar need to be lower than the temperature and mass scales of the bath, right? Okay, so what can this term look like? Well, it can look like basically you might think 4 types of interesting matter, but in fact 3. So you can have non-relativistic matter where the pressure, in fact, it's a bit subtle. You got to take the derivative of it's not the pressure would just be linear in the temperature, but the derivative of the pressure at constant chemical potential is in fact gives you the mass density. It's kind of a thermodynamic identity, and so a non-relativistic source is sourced by just this changing mass density. Radiation, well, pure radiation, pressure famously goes like T to the 4 and nothing else. There are no other fundamental constants in that leading order expression. This is tied to the fact that Nordstrom theory does not bend light. You just have nothing to couple it to. So in fact, pure radiation, when you differentiate with respect to the field, just gives you no source term. If you do have relativistic matter, right, if you don't have pure photon, but just fast electrons, you've got to go continue your expansion in terms of mass terms and go get the next to leading order term, which would give you an m squared t squared type of source. And then finally, you can have a relativistic interacting dark sector, which is a quark-gluon plasma or QED plasma, but it's the part of the pressure of the plasma that depends on things like the electric charge, the gauge couplings, the Yukawa couplings, etc. It goes like T to the 4, but basically this is dimensional analysis, right? The couplings are dimensionless, and you need a pressure, and you need the couplings to appear because you want the, well, because you're doing expansion in the coupling, so it has to be G squared T to the 4. Getting this proportionality constants, extremely challenging. But luckily, there's a whole industry of computing pressures of quark-gluon plasma and the standard model, etc. Okay, that does lead to a kind of a puzzle, which I think is interesting, which is, well, you've got an oscillatory equation here, and you're driving it with a power law source. How come I get on-shell production at all? Right? I mean, that, in other words, like, say I couple to the electron, mass, this is my vertex. Okay, well, as we know from QED, for example, a single electron traveling at constant velocity will not just spontaneously erupt a photon, right? So what's really at play here is that this is a gravity or curvature-assisted process. For h bigger than m, the propagator of the scalar receives significant corrections from the Hubble term. And it eventually decouples when h is less than m. So I'll get back to that statement and put more meat on it. But graphically, this is essentially what happens. You kind of have an electrostatic dressed situation in the early universe that somehow gets, the scalar gets liberated, softly detached from its source term as the universe crosses the Hubble equals m point, right? Okay. How to see that more exactly? Well, you're solving a time-dependent equation of motion with an arbitrary source. The tool of choice for that is to use as the Green's function, which is the solution to the impulse problem. You change the source for an impulse source, and then you do the solution, and then the complete solution is then an integral of the source term over the Green's functions. Very similar to what people do in EFT of LSS, for example. Now, first things you can check is that indeed, in the far future, the source behave like a decaying, but first of all, you might question if this procedure is even finite at infinite time, basically. Like if this integral converges as I take as I integrate from the far past to the far future, The answer is it does. It gives you precisely an oscillatory form with a finite coefficient here, where this coefficient, of course, from the perspective of a late-time observer, quantifies the late-time amplitude of the field, and therefore is tied to how much production occurred in the early universe. To go and compute this A, you have to do some work with the propagator. So you can go and get the propagator for the Klein-Gordon equation in radiation domination, and I've plotted it here. And what we see is first, well, past points. So this is the Green's function evaluated at late times as a function of the location of the source. And so what this says is, well, this is monotonically increasing, and so it says, well, past points have a reduced causal influence on the present, which makes sense. But another important feature is it becomes oscillatory after h equals m, which essentially, and importantly, it is a power law before h equals m. Therefore, if I'm integrating a source term here, if my source is monotonic, it's not going to pick up, it's not going to contribute to the amplitude of the field at any time at any source time later than h equals m. Which makes sense, is the statement that today h is very small. If I did have a slowly monotonic source, like if I want to produce the field in the lab today, I will need an oscillatory source. But at 30 time, it actually goes like a to the 4, specifically a to the 4 in a radiation-dominated universe. So this is basically the statement I meant. Like the source, the source we're interested in are also power law during the entire duration of cosmic history. They won't be integrated here. A somewhat useful reframing of the issue you can make is multiply and divide by h squared and actually use g times h squared as your Green's functions. And it's nice because then it looks similar to the behavior of a free phi in a standard misalignment mechanism, which just goes along with the philosophy that in order to produce a particle, you need a waveform that espouses the natural waviness of the wave behavior of the particle. So now we just have to go and basically compute this ratio here for all of our sources. So in the case of a non-relativistic source, as I said, the pressure is just the pressure you know and love, n times t. Being careful of differentiating with constant chemical potential, you've got that essentially the source relative to the gh squared Green's functions is monotonically increasing. And so it is largest at late times, but at late times the field has already started oscillating. And so non-relativistic sources are, moderately potent or not so potent at exciting the field. In other words, they're power law suppressed. In particular, if I take a scalar that is heavier and heavier, I'm moving this dashed line to the left. And so I have less integration time before the oscillation kicks in. And that results in a relic abundance that is power law suppressed. But importantly, this is for non-relativistic source. For example, the standard model after pair annihilation is largely non-relativistic, but another context that is very much studied these days is what if I have a non-relativistic dark sector coupled to this scalar? And the main conclusion here is that, well, you thought maybe you had a theory of dark matter with additional forces, but what you have on your hand is a theory of mixed dark matter. In this case, of course, because the scalar itself is a function of the number abundance of the non-relativistic source particle, the suppression is also, the abundance is also a function of the relative importance of the source particle in your cosmology. And so you essentially get that the dark matter today is a nonlinear, basically a nonlinear function of your source, the amplitude of your cosmology today. This is the last I will say about a dark sector probably, but the point is phi, remember, can be very light. In particular, it can be in the fuzzy range. So now not only do you have a mixed dark matter sector, you have a mixed cold dark matter, fuzzy dark matter a system. And well, that means that maybe not all of your dark matter clusters, and this is something that Marco and Diego looked at in one of their more recent papers, which is one of the big reasons why you get structure suppression in these kinds of models. Is that a correct characterization? Right. Okay, relativistic free massive species. So now we're talking about, well, I suppose you could be talking about neutrinos, maybe, but really, imagine a scenario where you couple only to the electron and not to the photon. So yes, in practice, you have a QED plasma, but the scalar does not see the photon. It only sees fast electrons. So now the source term relative to Hubble, well, another thing that will happen is eventually your relativistic, you will hit the temperature scale of the electrons, and so you'll become Boltzmann suppressed. And so what happens is the source term grows in amplitude and then is rapidly cut off. And so the source term relative to Grease functions looks like something like this. And this is sometimes characterized as kicks because actually if you plot it on a log linear plot, it looks a lot more like kicks because it really looks like a big bump all here. But what happens is that the source, the potency of the source is confined to sort of this region of maximal efficiency. Oh my God, okay. And so as a result, as a result, for example, in the case I've plotted it, you'll notice that the scalar is so heavy that it in fact misses the kick, right? If I had a light scalar, I would have coherent, I would take the full brunt of the kick, right? But if I have a heavy scalar, I'm losing more and more of the potency of the kick. And so what happens is you get that the effective misalignment angle is, again, power suppressed as the scalar becomes heavier than the temperature, sorry, the Hubble associated with the temperature of the universe at which the sector becomes non-relativistic. And then finally, the most interesting case is the case where phi modulate the sides of a gauge coupling or Yukawa coupling or whatever dimensionless coupling, is mediating the interaction in your interacting plasma. Because in this case, well, the pressure term goes proportionally to Hubble, suppressed by the size of the plasma, the coupling of the source theory. It will still eventually go away when the plasma again becomes non-relativistic. For example, when you hit lambda QCD, you no longer have a quark gluon plasma. When you hit the massive electron, you no longer have a QED plasma. When you hit electroweak phase transition, you lose a couple of bosons in your plasma, et cetera. But because the source essentially has no feature in the far past, you get only a logarithmic penalty for looking at heavier and heavier scalars, right? So essentially, your scalars in this presence of this source have kind of a sort of UV sensitivity. And so you get a relic abundance that is in fact proportional, within a function of the logarithmic hierarchy between the mass of the scalar and Hubble at reading. Yes? Yes. Yes. Mediated by the bath, you mean? Mediated by the bath. Right. Because scalar was coherent. Absolutely. So the effective. Mm, precisely. So we will only be able. Good. So like I explained, we will lose analytic control if the coupling is large enough that the field excursion sees these nonlinearity, right? And my claim is because this, I'll show a plot at the end, but because this sourcing is in fact quite potent, you get overclosures at extremely small couplings. And so you do get meaningful overclosure bounds, is what I mean. You get overclosure bounds within the regime of validity of that theory. Oh. Then the yes. No, I'm just saying that if the scalar says scatter, I can't treat it as a wave. Okay? No, you're will be a path. No, then would be scatter. That's correct. so in a sense, in a sense, these bounds. This is why the nature of these bounds, perhaps, it constrains a range of intermediate couplings, if you will. If the coupling's too small that you don't produce anything, fine, you have no upward closure. If it's too large that you lose analytic control, I don't know what to say. Well, sorry, you're right. You're right. Okay, good. So the other thing is, well, it doesn't mean it's going to thermalize, but yes, you end up in the regime where thermal overproduction. So another way of saying it is yes. So you become in the regime where thermal the right way to, if the particle becomes strongly coupled, the right way to talk about production is not that. It's the thermal. It's the thermal production, right? Yeah. Oh, it's in the backup slides. Good. So this is, for example, I think this is for coupling to the photon. The black line, and I need to specify a reheat scale, a reheat temperature. The black line is the locus of parameter space where you produce all of the dark matter today. The red region is where thermal effects would dominate this discussion. The purple region is the region where thermal self-interactions, in a sense, would dominate this discussion. Oh, absolutely. Absolutely. I should say in these units, everything that sits above zero is coupling this stronger than gravity, right? So good. So my claim is that yeah, it's for exceedingly feeble coupling, Planck suppressed couplings that you get these. Okay. So good. So I wanted to contrast with thermal production. Okay, I guess. Hmm? Hmm?
Because if you make it jump to higher, all the statement assume that you don't scatter even once over an apple time. Okay? If in an apple time I scatter, then I have just a Boltzmann distribution.
Right.
Okay? I don't have a way. Yes, even if you are, because yeah, exactly. So coherence is not only a matter of the mass, but it's also a statement about the
distribution function.
This company gets very high. Because you are coupled to something that is thermal. Yeah, so we constantly get a kick. But there's the fact that something else that is. Yes, it's not the self-coupling will not happen. No.
Yes. Yeah. So the right way to phrase the question is identifying precisely where notice that the coupling gets smaller here, but at heavier masses, for example. And so if the scalar is heavier, it requires less of a large field amplitude to overclose the universe, right? So your question is basically about this formula of ratios of omega in terms of the misalignment angle versus the mass relative to H equality, plotting it, setting that to 1, plotting it on that plot. And yes, you're right. The coupling is very small. The excursion is small, which is also why the field excursion is small, which is also why you don't have to worry about the values of the standard model changing appreciably during this dynamic, right? Good. So yes, so relative to thermal coupling, what I think is somewhat peculiar about this mechanism is it leverages the hierarchy of scales in the early universe. So in the early universe, T is very T is much, much larger than Hubble because the Planck mass is large. And so I drew all these, to be somewhat rigorous or semi-rigorous, I drew all these diagrams with everything getting dressed by Hubble. But really, I need to partition this diagram and instead, in a sense, in two, not thermal band, but in two sort of temperature sectors. One thermal sector, which is led, as the source is concerned, as far as the source is concerned, by the high temperature T, while the classical, the field, the scalar field obeys is driven by the scale h, which is much smaller, as opposed to a typical thermal production, where the scalar would also be driven by the thermal scale T, right? So the whole box would be hot, the whole diagram would be hot, whereas here, sort of a hot and cold diagram. Okay, so we've done single species sources. How do we deal with the universe as a whole? It's a bit of just of a bookkeeping headache. I mean, the source, because we focused on a linear potential, the source is also linear, and so it's a matter of decomposing the thermal history of the universe into its different phases of evolution, and then once you integrate out against the Green's function, the different source periods of evolution of the universe sort of just had coherently. And so it's to a certain extent, you perform the same exercise. You perform the same exercise as you do when you compute G star, the number of relativistic degrees of freedom in cosmology. You sit down and ask yourself, what is the appropriate degrees of freedom in that phase, in the standard model for that phase of evolution. Now, and another lesson, of course, was that when the phi enters through dimensionless coupling is when it's most phenomenologically interesting. And so you might say, okay, well, what if it just doesn't enter through dimensionless coupling? And that's where I would say, well, I suppose it depends what you think about where you define the theory. But if you're trying to couple your scalar above the electroweak phase transition, it's kind of a remarkable fact of nature that there's a single dimension one fundamental constant in the standard model, namely the Higgs mass squared. And so if you do couple to only the Higgs mass square, it means that as the theory reheats above the electroweak phase transition, you'll never, basically you're not going to couple to the gauge bosons, and you will not have, you will effectively truncate your production at H corresponding to the electroweak phase transition. However, I don't know, if you adopt sort of a probabilistic view of where this scalar enters the standard model, well, out of all the fundamental constants of the standard model, most of them are dimensionless. And so I would say, it's perhaps very likely that you couple through a dimensionless coupling. The other way around is if you're interested in viewing it from the perspective of experiments, most of the dimension one constants at the level of atoms, in fact, descend, match onto dimensionless numbers in the IR. So if you're interested about, you say, I don't care about what happens in the standard model, I care about what happens to, the proton. Well, as you enumerate the ways of coupling to the proton, most of them will go, for example, to G3 because the proton obtains most of its mass to lambda QCD, or it obtains its mass through the quarks, and so it would go to the quark Yukawas, et cetera, right? So this is, for example, the locus of overproduction plotted in the parameter space specifically for coupling G3, a strong coupling modulating scalar, as a function of the reheat temperature. As I said, essentially, the production is sort of adopts this universal feature, this power law, and then starts getting suppressed. So each of these kinks essentially correspond to H reheat, right? So you produce all light scalars whose masses is below H reheat kind of democratically. And then once the scalar masses, once you start considering scalars that are heavier than H reheat, then you get a suppression. And the remarkable fact is, yeah, I mean, you can get interesting constraints in space of very, very weak coupling where, your assumptions hold. Yes? Right. So BBN would be that line. It would be excluded. Yeah, it'd already be experimentally excluded. Yeah, the minimum line is already excluded. You can try to play games. So a lot of these bounds are in fact EP violation bounds. So you can actually try to focus on the the universal case. You can try to cook up the theory that would erase these bounds, but then that wouldn't be a a theory that couples exclusively to gluons. It would be a theory that couples to everything democratically. Yes. Yeah. So how to use this? How to use this plot? Yeah. I mean, one way to use this plot is if you do. Uh, you don't need the phi to be the dark matter to make useful use of this plot, right? Because this is saying cosmology is constraining the theory. So if I go in the lab and, for example, find something, where my cursor is sitting, then I would say, well, or say, I don't know, maybe let me pick exactly electroweak symmetry breaking. If I find something there, uh, unless there is a narrow band of maybe exact cancellations between the coupling, this would be very suggestive that the reheating temperature was precisely around electroweak phase transition, right? So it's also saying like if you're designing if you have strong prior beliefs about what H reheating can be, then this can inform, experimental searches, for example, etc. Right? Okay, so is that a compelling, good origin story for dark matter? I mean, I suppose I'll let you be the judge. I like that it's cold from production. I like that it's going to the question that was asked. We haven't done really the inhomogeneous perturbation story, which where would take the Klein-Gordon equation with the pressure perturbations. And so but for the simple argument that this is tied to the temperature of the standard model, it seems to me that this is likely going to give adiabatic perturbations. It can be quite heavy for H reheat I enough, meaning that it actually has some viability in parts of natural parameter space. Naturalness is generally a big problem for scalars. You can have a scalar that is light and with strong coupling, but because the reach of these constraints goes to such small couplings at large masses, you in fact do have some natural parameter space. Like Zach emphasized, you can also view it, a detection of any form, whether it's a detection of the cosmic relic or a detection of a force in the lab, would inform the reheat history of the universe. I personally like that it does not require inflation to misalign the field. The flip side of this statement is if I do have inflation, well, that itself places constraints on H inflation because of isocurvature productions and et cetera. Um, and in this case, morally, what would happen is the inflationary production would add to this thermal production. And so I can go back to the plot, but basically you can visualize the space where the thermal relic is more important than the inflationary relic, and et cetera. I've already talked about future work. So yeah, that was my message. I would say that feeble, meaning subgravitational strength, finite range, scalar mediated fifth forces, whether in the standard model or in the dark sector, are associated with a cosmological dark matter condensate from the early universe, process known as thermal misalignment. Depending on the coupling, this can be a potent mechanism up to H for masses of scalar masses up to H reheat. I would argue I would emphasize that most ways of coupling a scalar to the standard model will produce this, are likely to produce this relic abundance, because as I've emphasized, most of the standard model parameters are dimensionless. This is a rough, basically, this is the location of this red line that I've shown earlier, which basically says that for couplings as small as this relative to gravity, you can produce all of the dark matter today. And these considerations about producing relics in these models are also important for dark sector model building, because very light relics can affect structure through clustering or maybe things I haven't even thought of. So thank you very much.
volume. I want to go back to the other side of the source part, the basic part of the superquantum mechanics. If I understand correctly. If I, so my, okay, if I understand correctly, if the source is accelerated, time scales are figured out 10 minutes, so it's mass multiplication, then I have to take the
Yeah, that's a nice way. That's a nice way of understanding the H versus M hierarchy. Is
sources that are not necessarily
cosmological, but astrophysical, or that um, that's a very good point. I'm actually toying with that idea right now for if you've got whatever standard model particle um, the scalar is coupled to. If you look at that in a black hole environment, for example, as it accelerates rapidly towards a black hole, uh, as I've tried to emphasize, those are curvature assisted effect, right? And I mean, Hubble is one type of gravitational assistance. There are others. So you're correct. Yeah.
for the lighter case.
Yeah. The astrophysics pension of this, yeah.
So maybe it's a slightly crazy question, but do these core theories like violate gravity?
Good. Good. Okay, so I'm not an expert at all in these quantum gravity conjectures. I've asked myself the question. In all the ways I've talked to Matt Rees, for example, about this, and before thinking about this project. So, from his explanation, it seemed that the fact that there is a conserved charge played a key role in deriving that conjecture, right? Sorry, that there is a global charge. Yeah. The global charge associated, right? And that's why I had a slide emphasizing that in fact scalars do not have a global. There's no global U1 associated with a scalar, right? In other words, like um, if a black hole is charged, the weak gravity conjecture is something that has to do with the effect that by the time the black hole has evaporated, you can't have just charge changing place, right? And essentially, this is because if the black hole is charged, there's no other way for the black hole to dissipate the charge other than sending it out. But if the black hole is full of scalars, they're scalars. Sorry, they can annihilate. They can self-annihilate, right? I mean, there's no meaningful notion that there's a charge associated with that scalar. So it can just be. Now, to be fair, if you do Google, look up on the archive, weak gravity conjectures for scalars, people have attempted to formulate it. I understand also they're a bit. Yeah, I don't want to compromise. I think they're a bit on a less strong footing, especially in the case that, I think you can only, it's a statement to the effect that, one particle in the spectrum needs to have a particular charge to mass ratio, but, the other particles are, you just have to, you need to have a decay channel for black holes. Right. So, but that's a good point. That was also a concern with these models. Yes? Um, that's a good question. I suppose. So I don't know is the answer, or what the role of entanglement might be in discussing these dynamics. When you generally do these calculation in the thermal path integral formalism, you know the formula, the thermal field theory is a very powerful thing because it's to the extent that quantum effects are zero temperature effects, right? That have to do with virtual particles as opposed to physically existing particles, and then finite temperature effects, which are the thermal field theory formalism kind of subsumes all that into a single calculation. And so it's very hard for me to sort of peel off anything that would be inherently quantum. So yeah, I wouldn't be able to say there's a density matrix formulation for these potentials. Yes.
Can I ask you where it's located?
Ah, yes. So basically, these darkened regions, like if the scalar is very light, for example, I guess the color, uh, whether you look at in the variance that an inflationary field would acquire or the expectation value will be this darkened region. So for example, if this, right, if this were not already experimentally excluded, then the portion of that black line would essentially, be less informative than inflationary production.
So yeah,
Right.
it's production.
Right, 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 right. Or yeah, it's dominant in this wedge. Yeah. Okay. Well, thank you.